Guys, what's going on? So, welcome to Logic Bytes by AK, and today we are checking out the problem of the day in LeetCode. So, the problem is a stone game part 2. So, let's go into the description. So, here Alice and Bob continue their games with piles of stones. There are number of piles arranged in a row, and each pile has a positive integer number of stones piles of 5. The object of game is to end with most stones. So Alice and Bob take turns, with Alice starting first. Initially we have m equal to 1. On each player's turn, the player can take all the stones in the first x remaining piles where 1 less than or equal to x less than or equal to 2 into m, then we set m equal to maximum of m comma x. So the game continues until all the stones have been taken. Assuming Alice and Bob's play optimally, return the maximum number of stones Alice can get. Okay, guys, so initially we have m equal to 1, and at first Alice starts the game. So Alice have the options that he can choose at max 2 into 1 2 into m piles, right? So if if we take x equal to 1, Alice can choose 2, and if x equal to 2, he can choose these two, right? So if he choose these two, he can get 9, right? And if we have chosen 2, right? So x will be 2 and m will be updated with previously m is 1 and we choose x equal to 2. So then m will be updated to the value, the number 2. And from here, it's a Bob's turn, right? So he can choose at max a 4 mean 2 into m piles, right? So the m value is 2 and we have 3 piles, and at max we can take 4. So he takes all the possibles, 9 comma 1 4 comma 4, which is total of 17, right? Oh, it's 17. So Alice got 9 and Bob got 17. Is there any way to get more than 9 for Alice? Yes. So instead of taking two values at a time by Alice, he can choose one element which is x equal to 1, and after taking 1, Alice gets 2 stones and m will be 1, right? So it is previous maximum is 1 and x is 1, so the maximum is 1. So m does not change. So Bob can take a 1 stone, right? Mean, yeah, we have M as 1, so Bob has the chances of taking 2, 2 into M at max, right? So Bob can choose at max 2. So here Bob also plays optimal, right? So if we choose 1, so Alex gets more points. So what he do, Bob will take these two, which is total of 16, and the m value is updated to 2, and we can take x value at max 4. So Alice gets the last 2, and which is total of, which this is 8 and this is 2. It will be 10. So let me explain it more clearly with a painter. So okay, guys, let's understand the problem with in more detail with this example. So, Alice always starts the game at first. So, for every initially we are at zero index. So, we have the options up to at max we can choose 2 into m. So, I for x the values are 1 and 2, right? So, we can choose a first element or at at max you can choose first two elements or a single element. So if we choose one element, Alex can get 1 points, right? And for every time when we choose one element, the maximum value will update with x, right? Maximum of m comma x. And here x is we choose one, right? So the x value will be one, and previously m value will be one, right? So m contains maximum of a previous m and previous x. So m does not change; it gets as one itself. So after Alice getting first pile of stones, now it's Bob's turn to play. So Bob starts. Sorry, sorry. Bob starts from second index. So Bob has at max chance of a two, right? Because the m value is one, and he got the options x equal to one and x equal to two. To play optimally, Bob can choose a one or a two elements. So let us say he choose two elements. Guys, now Bob can take these two. So he gets a total of 5 points from here. So now it's Alice's turn to play. So Alice starts from index 3, and Bob taken two values, right? So the maximum will be, see, sorry, the m value will be updated to maximum of 1 comma 2, right? So the m value will be 2, m equal to 2. So it means Alice can choose a 2 into 2, right? I mean, at max, he can choose a 4 piles. So he can choose all of them. Wait a minute. So he can choose all the remaining files, right? So here we have to find the sum of all the pairs at last, right? So 4 plus 5 plus 100. It means we have to iterate from a current index to n when our m into, sorry, 2 into m value plus current value is greater than or equal to n. We have to find the total sum, right? So instead of iterating over these elements and calculating the sum, what we can do, we can, uh, I mean, we can define an array which stores a suffix, a sum of elements, right? So let's make a suffix array. So when we are at a current index, and the current index has the options like, it has options of more than the last elements, right? The last elements are 3, and we have options for x up to at max 4, right? So at that time, we have to return the sum of elements of last three, right? So how can we get last three elements a sum? We can get by prefix array, right? If we have a prefix array, we can just return the current index value, right, of suffix sum array. So this reduces our iterations for every index. Let me break down this problem. So, firstly, we calculate the suffix array for given piles of array. And so, what is the overall logic here? So, if you are, wait a minute. So, if you are at current index, let's say I, and you have at max, let's say 2 into m possible. You can take at max 2 into m piles, right? From 1 to 2 into m. It means So we have to consider every possibility, right? So from X, if you choose one pile of array, you can get some score, right? I mean stones. Let's say stones. And if you take two, you get some result. And if you get three, you get some, let's say, some stones of X, and you get some stones X, and you get some stones Y. So these might be different values. So what you are doing, in some cases, you have to calculate or iterate over repeated subproblems, right? It means so for every index, I mean, when you are at current index days, if you choose the first element, you can get at maximum of 2, right? So it means if you store at current index, and if we have our x value as x, you can store the maximum score can get from current index I with by taking the x stones, you can store the result here, right? So what we have to do, we have current index as the possibilities of n indexes, right? So where n is a length of files, and what will be the our at maximum we can take an array of stones, right? So the size of the data structure that we store, the maximum stones that we get when we are at current index, and by taking the first x stones, we store that result at index of, I mean array of current of x, right? It means it will be a 2D array, and we store it in that, right? So what we have to do, and coming to our logic, Alice, we have to return the maximum number of stones that Alice can get by playing optimally with Bob, right? So here, what is the main logic? Alice has to get a maximum score, I mean, let's say maximum, and by giving a minimum score to Bob, right? So if we give or if we just leave minimum score for Bob, he gets less number of stones and we can get maximum number of stones, right? So this is min-max strategy, and let's go with the possible steps approach. So guys, so we take a function which gives a maximum number of stones at the current index by taking mean the possible ways for x is m, and we need a memo, right? Memo or 2D array. So in this example, we start at, wait a minute, we start at maximum of 0, right? Our starting index will be 0 and the m value is 1. So the memo stays the same. So for when we are at current index 0, what are all the possible ways when m equal to 1? 2 into m, right? So for m we can choose for at index 1 and at index 0 we can choose, wait a minute. So if we choose 1, we return the maximum score at 1 with m value 1 and memo, right? So the here x is 1 and m is 1, and we update m value with maximum of 1, right? Which is a maximum of 1 comma 1. And the other case is, and let's say here maximum stones, it is a function stones, and when we are at index 0 with the value m, you can take x from 1 to 2, right? So if we choose 2, the function is we have x value as 2 and we update m with maximum of m comma x, so which is maximum of 1 comma 2, so the m is 2 and we return memo. So and for this function we are at index 1 and we have the m value as 1. What are all the function calls we can make? Maximum of, if we take the m value, the x value as 1, we can go up to, and we are already at index, it will be our current array, and the x value will be 1, right? So current index plus I, it will be 2, and we have maximum as 1, right? So the x is 1. So it will be memo. And for this, if we choose 2, the maximum will be 3 and the m value updated 2 and we get memo, right? So just a moment. Okay. So let's this change with the color and another color blue. And these are for blue. And blue for blue. And for this red color function, we make a function calls and we are at current index 2 and we have m value is 2, so what will be the x value? 2 into 2, right? So it will be 4, and we are at current index of 2. So if we have these maximum, we can return the suffix array of current index, right? When we can choose at max number of element, at max last number of elements, we can just return what we can return, a suffix array of current, right? And this function call will return 1 1 2 to the main function call, right? So the steps here is when current index plus 2 into maximum is less than or equal to files dot length, we return, sorry, we return suffix array of current index, right? So this is the one step. And so uh, okay, now we continue this process until or unless we reach it to the end of the array, right? So this function handles that condition. When we reach to the end of line, we return the current suffix array. And so as of now, we are making a recursion call. So if current index is 2 and the m value is 1, and if it is already there in a memo, we return that index, right? So which is, if memo of current index and the m value is already calculated, which means which is greater than 0, we return memo of current and m, right? So if it is already updated value and we don't have to make a function call for that, right? You can just return. It means we are stored the repetitive subproblems value in memo index. And after calculating this, we have to return the minimum score to Bob, right? So how can we return the minimum score? And by iterating over subproblems, we find the minimum result, let's say RES, which is RES equal to minimum of these function calls, right? Let's say, shit. Let's take, wait a minute. So these are the subproblems of for a function call. I mean the recursive calls. So it will be, wait a minute. So if res equal to, we take a minimum of these function calls, and by taking the minimum, how can we return? And it means we have our minimum value, which is to be given to Bob, right? So if we have minimum value, let's say 109, have it. If you have minimum value 109, what we have to do? We subtract that from our, let's say it is current array. So you got the minimum value from these, let's say which is 100, the minimum value, and you subtract these 100 from 112, you get the minimum value from these, right? Which is of 12, which Bob can get after completion of Alice game at this stage. And we subtract these 12 points from Alice, right? So Alice can get 100 points at this current index, and Bob can get 12 points. So which is, we are given Bob a minimum value and we got maximum value for Alice, and at the end of our function we return this. So let me uh, explain it more clearly with the code. So let me write a code. Firstly, what we have to need, we need a suffix array, right? Let me create a suffix array. Let's say suffix, which takes the length of files dot length size, and we need a function maximum stones, which takes a suffix array as input, and our current index will be 0, and the initial m value is 1, and we need a data structure to store the maximum stones can get from current index, and when m value will be m. So we take a memo data structure. Let me define memo in memo equal to new int of files dot length. So the current index ranges from 1 0 to n minus 1, right? So as well as the uh, we can take first m values. It means the m can be n, right? So we take files dot length for this also. So the maximum stones returns the maximum score. I mean maximum stones that we can get when Alice starts the game. So let me write the function. So public int max stones, which take a suffix array, let's say sfx, and we have our current index, and we have m value, and we have memo data structure in our function call. And that's the function. Let me calculate the suffix array. How can we calculate suffix array? For suffix array, the last element would be the last element of files, right? So let me define a variable here, int n equal to files dot length. So it will be n, will be m, it will be m. So for the last index of suffix array, it will be the last element itself. So now we iterate on I equal to n minus from last second element to the first element. What we will do? We store the previous sum of, I mean the next sum of one with in a suffix of I, and we add the current element, right? So this will be our suffix array, and we calculated suffix array. We are at initial at current index with the value m as 1, and we define a data structures to store the maximum stones can get when we are at the current index and this element. So here we handle this case when our current index plus the number of elements at max we can take is 2 into m, which is greater than or equal to suffix dot length. We return the memo value of, oh sorry, we return a suffix of current, right? But we are already discussed in this previous example. So, and if memo value is already calculated, which is greater than 0, by default it will be 0. If which is it is not equal to 0 means it is already calculated, right? We don't have to calculate it again. So we return memo of current and m, and to store the minimum score, which the score is assigned to the Bob. Let's take RS or min score, which will be initially int max. So we iterate on what are all the values of x. Values of x will be x less than or equal to 2 into m, right? So x plus plus, and we take return, the minimum value from previous RES, and we need to calculate the maximum number of stones when we are at current plus x index, and with the m value, and with the m value math dot maximum of x comma m, right? And we know that we know a function which returns maximum number of stones when we are at current index with m options, right? So, and we need to calculate it again here, right? So, we need maximum score by taking a suffix array, and we are at a current index plus x index, and the m value will be updated with maximum of x comma m, and we need a data structure. So this will find the minimum score for a function call by taking x options, and the minimum score will be our RES, right? This RES holds the minimum score, and this minimum score is given to Bob. And what will be the maximum score is stored at memo of current of m will be stored at a suffix of current index minus RES, right? So let's go with here. So when we are at 122, we got the minimum 100. We subtract this 100 from 122, which is suffix of current, and Bob can get 12, Alice can get 100, right, which is maximum score. And we store the maximum score at a memo of current index and with the M options. And finally, we return memo of current of M. This recursive function call may goes to the every possibilities at every index with the options M, and it will return the optimal, I mean maximum number of stones. Let's compile it again. Here, the function the maximum stones like Steven stones. Check it again. Sorry, it got wrong answer. So sorry guys, here it goes on. We have to update x with I mean m value with maximum of x comma m value. So I did a mistake there. So let me run it again. Yeah, it works. And I think the complexity will be maximum more than n square because for every element there can be m options, right? So the complexity will be greater than n square or it can be n cube. So yeah, it is n square. Let me check the space complexity. It will be n square as well because we are creating a memo to be array with the size of n by n, and this can the space can be optimized, I think so. So thanks for watching, guys. See you in the next lecture. If you have any queries, please feel free to comment down in the below, and yeah, you can give my feedback on lectures and explanation so that I can improve myself. You can give me any suggestions regarding the teaching way of teaching so I can improve myself. That helps me so much. And thanks again for watching this and see you in the next lecture.